Welcome to this tutorial. In our last segment, we had looked at an introduction to torsion, and I mentioned the torsion equation. So in this video, we are going to see how to derive the torsion equation. Just to recall what the torsion equation looks like. So we have T over J is equivalent to uh, tau over R, and that is also equivalent to G theta over L. So these terms are interchangeable. So you can either have G theta over L in the middle or the other way around. So today we are going to look at how to derive that equation. Now to kick us off, this is a shaft. So if you can see, this is the length L of the shaft. Now if you look at this from this other side, that is the end view, assuming that this is your eye, and you're looking at the shaft from this end. So you're going to see a circular cross section, and for this analysis, we're going to take R, capital R, as the radius of the shaft. Now, assuming that the shaft is being twisted in a clockwise direction, or by a clockwise twist shown by this direction, and we take a point on the circumference of this circular end and mark it A prime. So when you mark it A prime, after some time, after twisting, you're going to have A as the other position, or the position of that point along the circumference of this shaft. Now, we're going to project these points to this end here. So we're going to have A prime. Now, ideally, this is supposed to be so we are supposed to have A at this point, and then A prime to be the other part, or the other position after twist. So we are going to extrapolate, or rather extend these ends to this line, and we're going to come up with a right angle triangle that is A. So A prime O. So that is the triangle that through which we are going to base our arguments, or rather derive the torsion equation. Now this length A will be A prime. Okay. And we have some angles here to talk about. So we have theta, and in this other case we have phi. So from our basic knowledge of calculating the length of this arc A prime, so the length of the arc A prime is equivalent to, so the length is equivalent to, take R multiplied by theta. So we're going to say R multiplied by theta. So that is how we get the length of the arc. Now the length of the arc is equivalent to AA. So we say A prime equivalent to R theta. Okay. So that is the first equation that we are going to get under this. First of all, we have gotten this length A prime, and that is equivalent to A prime, or R theta. Now, if you consider this right angle triangle A prime O, then we realize that tan, or the tangent of phi, equivalent to A prime A, or the other way around, divided by L. We are going to consider this angle very, very small. So we say since phi is very, very small, we therefore have tangent of phi being equivalent to phi. And that leaves us with one thing. So this equation here will be phi is equals to A prime over L. So that is how it will narrow down. But one thing we know is that this angle phi is equivalent to what we call shear strain. So this angle phi here is equals to shear strain. Now, up to here, I'm going to introduce another term known as G, or modulus of rigidity. But how does it relate to shear strain? So shear strain is equivalent to shear stress tau over shear modulus, which in this case is equivalent to G. So that is how we can get shear strain. So it will leave us with this equation tau over G. So from here, we know that A prime is equivalent to what? R theta. So if we substitute the same in that equation, we're going to end up with phi is equivalent to R theta over L. And that can be easily equated to this other part of the equation. So we're going to have R theta over L is equivalent to tau over G. So cross multiplying this will give us this equation rewritten as follows. So we're going to have tau over R is equals to G theta over L. Now this will be the first part of the torsional equation. Okay. So we're going to have it as equation A. So let us keep this and see how we derive the other part of the equation.